Hi everyone, my name is Oliver Love. I'm a senior software developer on the DigitalOcean Kubernetes team. And today, in the next 15 minutes, I'll talk to you more about Kubernetes reliability and best practices. Before we start, it's important to understand that the meaning and scope of reliability can be different from a small and medium-sized business compared to an enterprise. As you probably know, SMBs often have limited resources, smaller scale deployments, which represents unique challenges in ensuring reliability of their Kubernetes system. In this talk, our focus is primarily on SMBs scale clusters, so it's typically clusters that have 500 worker nodes and less. So here's the agenda for today's talk. So we'll start with a broad overview of the reliability challenges. We'll cover how right-sizing your pod's resources is important. We'll go over Kubernetes probes and health checks and their different use cases. Then we'll cover two different deployment strategies for your day two operations that you can easily add to your CD pipeline. We'll cover pod scheduling and spread constraints and how they can help you make your system more reliable. And finally, we'll cover how you should be using unique tags to help debuggability and prevent issues. So let's start with the reliability challenges that we typically see in a Kubernetes cluster that have their reliability impacted. When things do not work as intended, the problem can manifest in various forms. For example, your pod can be in a crash looping backup state. You have set up incorrect resource limits or requests in your pod spec configuration, which leads to termination of your pods and could cause downtime for your users. Or you could have misconfigured dependencies, incorrect load balancer, or ingress configuration that leads to your traffic not being routed properly to your backing application pods. Also, the latency can be higher for your customer because your pods are being resource limited and they don't have enough resources to do the task they are required to do. To help fix those issues, we need to implement effective reliability in our Kubernetes environment. This requires a structured approach and adherence to Kubernetes best practices. We won't be able to cover all the best practices in this talk, but one of them is the right sizing of your pods. It is important when deploying resource inside your Kubernetes cluster that you indicate how much CPU and memory RAM you want to allocate to your deployed resources. By describing those constraints, you're helping the kube scheduler control plane components make better bin packing decisions when assigning your pods to your worker nodes. Then, once your pods are assigned on worker nodes, the kubelet component will then ensure that the requests and limits specified on the pods containers are enforced. This means that you need to ensure that your biggest DOKS worker node pool contains worker nodes that can accommodate for the specified CPU and RAM request, or else you could end up in a scenario where your pods cannot be scheduled on any worker nodes and could result in downtime for your application. Also, since the request value will guarantee the reservation of those resources, it is important that you're not over-requesting and pay for extra resources that you don't need, or that could probably be used for other workloads. Next, we have the CPU and memory RAM limits. So Kubernetes will enforce those limits and prevent deployed resources from using more than what they are given. It's important to understand, but CPU and RAM limits, they behave differently. When the CPU limit is reached, your pod's container will be throttled. So this throttling could lead to degraded performance of your application, especially if they're running against those CPU limits values for a prolonged period of time. That said, even if that throttling could lead to degraded performance, the containers won't be terminated or evicted by the container runtime since the CPU is a compressible resource. Your application can remain accessible, but the performance will likely be altered. In this scenario, if you're always pushing against your CPU limits values, you should revisit those limits to prevent throttling. On the other hand, by omitting CPU limits, processes will be able to use any additional CPU capacity on the worker node. In contrary, when CPU limits are set, application may be CPU throttle even when the node has otherwise idle CPU capacity. As a general rule of thumb and as a best practice, we recommend that your application omits the CPU limits entirely unless you have strict needs that implies setting them. On the other hand, when the pod memory consumption limit is reached, if the container allocates more memory than it is allowed to, the container will become a candidate for termination. You will see a status of out of memory on the pod status when that termination occurs. This behavior is really important to understand because terminated pods could cause some downtime for your applications until the new pods are scheduled and back in a running state. Next, we'll cover two important Kubernetes probes for improved reliability. The first probe is the Readiness Probe. This probe indicates if the container is ready to accept and serve traffic. Usually, application will have some tasks to do when they initialize or during their runtime. For example, they might pull secrets from an external vault, load their cache, interact with different services, and do other tasks which should prevent them from receiving traffic. That said, we don't want to send traffic to those pods or containers until they're fully ready to accept and serve the traffic. If those pods are targeted by a Kubernetes service, like in the example in the picture on the right, and they are reporting that they are not in a ready state, like pod number 1 in red, they won't receive traffic, and this is what we want. We only want pod number 2 and pod number 3 to receive the traffic, since they are the only pods ready to accept traffic. Something that is also important is that omitting the readiness probe on a pod container definition, backing a Kubernetes service, like in the example on the right, by default will consider the container as ready and will immediately be considered for receiving traffic. This is a scenario we want to avoid since it could result in errors in your system for a brief period of time until the container finishes its bootstrapping. As a best practice, if you have some bootstrapping to do at the beginning of your application, you should add a readiness probe. Next, the second probe we'll cover is the Liveness Probe. So once your application is running smoothly, we'll still want to ensure that it stays that way, and if we detect potential issues that are unrecoverable and would require a pod restarts, we can use the Liveness Probe for that scenario. So this probe will periodically check if your application health, and if the check fails, it will terminate the pod. This is really powerful, and a typical use case for Liveness probes is for temporary mutation of a detectable condition that can only be handled via restart. We can think of memory corruption, a memory leak, deadlock scenarios. We can use the Liveness probe to restart those pods and then gather some metrics and logs until the root cause of the problem can be found and fixed. Finally, something that you should be aware is that Liveness probe should not have external dependencies or logic inside them. The last thing we want to introduce in our cluster are cascading events that could cause many applications to have their probes fail, which could lead to unresponsiveness and a lot of pod restarts. We recommend that Liveness probe's logic does not interact with external components, APIs, or third-party services, where you could have one failure that could cause many applications to fail. Also, if that failure is now repaired, but it occurred during a really prolonged period of time, or pods that had logic interacting with that external component could be very far in their exponential backoff restarts loop, and it will be even longer until they are fully recovered and back in a running state. This could impact your customers and add to the unreliability of your system. Next, we'll cover two deployment strategies. So the first deployment strategy we'll cover is the canary deployment. A canary deployment rolls out a small set of replicas with the new release and monitors the behavior with production traffic. If the new rollout is behaving correctly, we can increase the number of replicas using the new version. If it is the opposite, we can quickly revert those replicas. And then we can gather some useful information on the failure domains from the logs and metrics. If an issue was detected on the canary deployment, we can be assured that it only affected a small percentage of the production traffic and reduce the blast radius of that deployment. In the Kubernetes context, we'll have the following setup. As you can see, we have the green deployment on the image on the right with one replica with the new version that we want to introduce. So this deployment will receive 10% of the traffic since it's only 1 out of 10 pods backing the Kubernetes service. So both deployment blue and green are backing the Kubernetes service since they share the same labels. As you can see, the green canary rollout percentage can easily be changed by increasing or decreasing the amount of replicas of the canary green deployment. Depending on your application needs and the logs and metrics that you gathered by this deployment initiative, you can determine the actions to take by reverting or pursuing the completion of the new version. This can be easily added to your continuous delivery strategy and can be easily done in your DOKS cluster. Next, another rollout strategy that can be easily set up with DOKS is the blue-green rollout strategy. With this strategy, we introduce a new version by having 2 separate deployments. One deployment with the new version, the green deployment, while the other contains the current version, blue. As you can see, just by changing the Kubernetes service selector field to match the new V2 version labels, we can redirect the entire traffic to the green deployment V2. Depending on our metrics and logs that we gathered, if our tests are successful, we can drop the blue deployment, the old version, and continue with the green deployment, the new version. In the event that the tests are unsuccessful, we can easily revert back to the blue deployment by switching the Kubernetes service manifest labels to point back to the V1 field. And then we can tear down the green deployment and review what went wrong from the gathered metrics and logs. Next, we'll talk about pod spread constraints. So in DOKS, your cluster consists of one or multiple worker nodes, droplets, running your applications. This means that if you have application pods that are not spread out to one or more worker nodes, they could be easily impacted by a failure on the worker node itself. Also, since the DOKS platform supports the last 3 minor Kubernetes version, eventually your cluster will have to undergo a cluster upgrades to the last supported DOKS version. This will trigger a rollout of your worker nodes and could cause some reliability issues if you don't spread your application throughout multiple worker nodes. So this spread issue could also surface when recycling manually worker nodes or if you are using node autoscaling. So this issue can be solved by using pod topology spread constraints. So this is a Kubernetes feature, and it's really powerful since you can control how pods are spread across your cluster nodes. If we take an example of a DOKS cluster with 3 worker nodes running a deployment app1 of 4 replicas, we want to avoid the following scenario in this image on the top right, where node number 1 becomes a single point of failure for app number 1. If a recycling event, a cluster upgrade that caused node 1 to be drained, or any other issues that could happen on node number 1, the time that Kubernetes will take to reschedule the app1 on another worker node could lead to application downtime and reliability issues during that rescheduling. So the picture on the bottom right addresses these issues by using topology spread constraints in the deployment description. This way, we can spread our app1 to multiple worker nodes, reducing the risk of a single point of failure from worker node number 1. Finally, for the last best reliability best practices, when creating a new node, the default image pull policy in the container specification ensures that the image is pulled only if it doesn't already exist in the node where the pod is scheduled on. This can lead to inconsistencies if you reuse the same tag, such as latest, for different builds of your applications. Consider a scenario where you build your code into an image, you push it to a container registry, like the OCR, using the latest tag, and then you create a deployment using that tag in your DOKS cluster. The first time you deploy your pods, all the nodes will pull the image from the registry since they don't have it cached locally. However, if you update your code, build a new image, a new container image, and push it to the OCR registry using the same latest tag, then you trigger a new rollout using the same tag. The pods running on nodes that already had the previous latest tag will continue running the old code without you noticing. However, any pods on a new node will pull the latest image, resulting in inconsistent application versions. So to prevent these inconsistencies and ensure that your pods are always running the intended version of your application, it is highly recommended to use semantic versioning tags or the commit SHA to uniquely identify each build. This practice helps differentiate between different binaries and configuration, preventing collisions and ensuring that the correct version of your application is deployed consistently across all pods of your cluster. So this is the end of my talk. I hope that you learned something interesting about Kubernetes reliability and best practices, and that you could introduce some of them and some of the concept in your DOKS cluster. My name is Oliver Love, and I hope you enjoy the rest of DigitalOcean Deploy 2024.